All right, everyone, welcome back to our second lecture video. In today's video, we will be covering chemistry, or the chemical level of structural organization. If you can remember in the first lecture video that I posted earlier this week, we talked a little bit about these levels of structural organization. And all they really are is a template for us to understand the body at different levels. So the chemical level is our first level, or the smallest level, that contains atoms and molecules, and we're going to talk today about how those atoms and molecules will interact with each other. So in today's class, we are going to talk about some of the concepts of chemistry. Now, I want to make this very clear. Those of you that don't like chemistry, I understand we didn't sign up for a chemistry class. This is anatomy and physiology, so we're going to keep this light. But we do have to have some understanding of chemistry if we're going to understand biology. And we're going to understand anatomy and how the different structures are going to look at each of these different levels of structural organization. So we will talk about a few of the concepts of chemistry, and we're going to talk a little bit about matter. What is matter? What types of states of matter do we have, and how is it organized? We're going to mention a few different types of chemical bonds and a few different reactions that are going to help to form those chemical bonds. We're going to learn two major types of reactions that are going to help to build up larger molecules and break down larger molecules into smaller molecules. So we will talk a little bit about chemical bonds and reactions today as well. The last major portion of this presentation is going to compare and contrast our inorganic compounds with our organic compounds. So as we move on, we're actually going to talk a lot about carbohydrates, and we're going to talk about lipids and proteins and how all of those macromolecules or organic molecules come together, and that's going to set us up for everything else in this course. Understanding that the cell is made up of different amounts of these macromolecules. That's going to be a very important concept for us as well. So we'll cover that towards the end of the class as well. So, as we look at chemistry, as we understand what chemistry is, and we can see up here that chemistry is the science of matter. We're studying the physical matter in front of us. This is, the way that we can pick up anything off of the ground, and we can say, what makes this thing up. As I stand right here, I'm holding my cell phone, and that is, I question, what types of molecules are found within this cell phone, and so everything is made up of matter. Matter is just anything that takes up space and has some amount of mass. So, not to get this confused here, mass is essentially the amount of matter something contains. So, how much of this substance is there? While weight, on the other hand, is actually referring to the force of gravity that acts on that mass. So, those are often confused and used interchangeably, but they are not quite the same thing. So it's important to keep in mind our definitions as we talk about chemistry. I definitely, for those of you out there that are sort of frightened by Chapter 2's video, I didn't like chemistry very much the first time I took it either. And so I'm going to do my best to make this as straightforward for you all as possible. I don't want to make this any more difficult. Again, you guys didn't sign up for chemistry, so we just want to touch on the basic elements that we're going to need for anatomy and physiology. So, matter exists within three forms, and we've likely heard about this since we were young in our younger science classes. But we have solids, liquids, and gases. And even though this is a fairly simple idea, all of these different states of matter, as we will call these are our three states of matter. These different states refer to matter based on, the temperature that our substance is, or how much pressure is going to be found in a particular system. So all of those things relate to what state of matter our particular particles are in. So for example, temperature is one good example. If we were to think about water, if we were to put water in the freezer, that's going to seriously decrease the temperature of our water. And it's going to decrease it so much that our water is going to freeze and it's going to become a solid. But when we take that ice out of the fridge and let it sit, on the countertop, or perhaps in a beverage or something of the sort, that's going to melt as the temperature rises. And if the temperature gets really, really hot, like when we are, let's say we take those ice cubes and we put them in a pot the stove and we start to apply heat, that's going to eventually turn our matter to gas. So we will be referring to matter in these three ways throughout the course of this presentation. Now, don't be frightened here. This is the periodic table of elements. You do not have to memorize every single one of these elements here. There's quite a few, but the periodic table refers again to our composition of elements. And so elements are sort of our simple form of matter that cannot be broken down by any other chemical means. So the way that we look at our elements is they are very, very simplified versions of matter. So again, I don't need you to know every element here, but there are a few that I'm going to want you to note. So our first element on the periodic table is hydrogen. Hydrogen is going to be one of the most important elements that we learn about this semester. We'll need to know carbon. Carbon is sixth on the periodic table, so carbon is going to be very important. We're going to need to know nitrogen, which is number 7, and oxygen, which is number 8. And as we go through these, there are going to be more and more that we will learn. Sodium, for example, sodium is abbreviated with Na. That is number 11 on the periodic table. And chlorine is going to be another one. Chlorine is number 17. So we're going to talk about some of these today, and their numbers they do mean things. We're not just we didn't just arbitrarily throw these all together and make this oddly looking shaped periodic table. The periodic table is arranged in this manner for a particular reason. So we're going to go over how we can read a little bit of the periodic table and how we can assess information from the periodic table when we're talking about our molecules, our elements, and different types of chemical bonds. So as I mentioned earlier, elements are substances that cannot be split into any more simple form of matter by ordinary chemical means. If we were to travel to Geneva, Switzerland, and go to the particle accelerator that's found over there, we'd be able to perhaps break our elements down a little bit more readily. But no ordinary chemical means can split our elements at all. So these are one of the most simplified versions that we can view our different elements and matter as a whole. So these are four different elements that I mentioned on the last slide that are very, very important here. So these are going to be some of our major elements that we see. Oxygen is given the abbreviation O, carbon is given the abbreviation C, hydrogen H, and nitrogen N. So most of, especially the more the earlier elements that are on the periodic table, these different elements are going to be given most of the time the abbreviation of the first letter of their name. But of course, as we go back to this picture, you'll see that sometimes these abbreviations can get a little bit more confusing, and that's all right. We won't have to deal with anything overly complicated. Most of the ones in this class are going to be fairly straightforward. So again, you remember that carbon is C. We do have chlorine, which is abbreviated with Cl. I think the most confusing one we'll have is Na for sodium. So Na is going to be our sodium abbreviation. Now I'm not sure exactly why they abbreviated sodium with Na, but I believe it has to do something with either the Greek or Latin spelling. I can never remember which it is. But for our purposes, we will just need to know that Na represents sodium. So these four elements here are what are called the major elements. These are the elements that make up the majority of all of the matter within our bodies. So these four make up 96% of all the matter that is found within the human body. I think that's pretty outstanding that we have only 4 elements that are making up most of our bodies. There are going to be many other elements that are found within the bodies, but they are not going to be found as readily as these ones will. So as we talk about the chemical level of structural organization, we need to be able to break down our elements into their most simple form, and those are called atoms. Atoms are the most simple unit of matter, our most fundamental type of matter. So if we were to break up our elements, if we were to take a single element of hydrogen, we would have one hydrogen atom. So an atom is the smallest particle that, with the exception of subatomic particles, but it's the smallest version that we can have an element within. So there are subatomic particles that do make up atoms. There's been a lot of research in this field, and we have as a human race, we have broken many different particles into smaller versions of other particles and such. But atoms are the smallest unit of matter that retain the properties of a particular element. So when we start to break up these atoms, our elements lose their particular properties. So the subatomic particles are going to determine what element our atom belongs to. So when we start to break up these different particles, we're going to have different arrangements. But as we look at these, we have three major subatomic particles, and those are protons, neutrons, and electrons. Now it's important to note that certain of these particles will have certain charges, and they're also going to be located in certain places as well. So protons will always have a positive charge. They will have a +1 charge. Electrons will always have a -1 charge, and neutrons will have a neutral charge. So if we look at this example here, you'll see that we have a lot of these different particles that are found right in the center of our atom, and then we have this blue thing that's sort of wrapping around. We'll call that the electron cloud. That's how we refer to this. So there are many different templates. People have been trying to discover the structure of an atom for a very long time, and through those struggles, there were many different templates of what people thought they looked like, and certain templates give us a better way to see atoms than others. But one of the things that we can see here is that we have a lot of particles in the center, and we've got this blue cloud around the side. So this center portion here is called the nucleus, and within the nucleus contains protons and neutrons. You can see that indicated here. So all of the protons and neutrons within every single atom will be found present in its nucleus. The electrons, however, are going to be found in this cloud, hence why we call this the electron cloud. And you can see this example here, this electron shell model, shows us that we have this nucleus in the center with the positive protons, the neutral neutrons in the nucleus, and then around the outside here in the electron cloud we have these darker colored electrons. So there are different energy levels at which our electrons are going to be found at, and there's a lot that can go into chemistry. But again, we want to keep this fairly straightforward. So the overall structure of our atom is going to be shown here, with the protons and the neutrons found in the nucleus, and the electrons found within the cloud. Now, based on how many protons, neutrons, and electrons are found within every atom, that's going to determine what atom we have. That's going to determine how atoms are able to combine with each other and form new molecules. So we're going to talk about that as we progress here. But first and foremost, before we go any further, I should say, I want to touch on what atomic number is. So this is a very, very important concept. This is, in fact, so important that I have written the definition of the atomic number 3 different times here in 3 different ways. So all of this, I know there's a lot on this slide here, but this is all essentially saying the same thing. So essentially, the atomic number depicts the number that we see in every element on the periodic table. So every element has its own number on the periodic table, and that number is going to be the atomic number. So if we go back up to this picture here, we'll see that hydrogen was number 1. So hydrogen has an atomic number of 1. This is helium. Helium has an atomic number of 2. Carbon has an atomic number of 6, and so forth. So each element is given a different atomic number based on where it's located at the periodic table. So what the atomic number is telling us is how many protons are found within an element. So for example, hydrogen is going to have 1 proton because it is number 1 on the periodic table. Carbon is going to have 6 protons because it is 6th on the periodic table, and so forth. So the atom's atomic number tells us how many protons are in a particular atom. And the amount of protons within an atom tells us which element that we're looking at. So the only real major difference here between hydrogen and helium is that hydrogen is going to have 1 less proton than helium. When we take 2, if we have a single proton, that's going to be a hydrogen atom. So it's I think that's fairly straightforward. We just have a single proton is going to be our hydrogen. But the minute that we take 2 protons and we stick those 2 protons in 1 atom, that's going to now give us helium. So again, as we look at this slide here, Every single atom of the same element will always have the same number of protons in its nucleus. There can be differing numbers of electrons, there can be different numbering of neutrons, and there can be different numberings of protons. But if you change the number of protons, you're changing the exact element that we're talking about. So as long as we are referring to carbon, you will always be able to know that there will be 6 protons within that carbon atom's nucleus. So the amount of protons that we have in our nucleus, again, is called the atomic number. That's what we're referring to. And the atomic number tells us which atom or which element our atom is. So we should say it that way. The atomic number is telling us which element our atom belongs to. So there can be differing numbers of protons, neutrons, and electrons within an atom. But if we change that number of protons, that is going to give us a different element. So carbon, again, you can see has 6 protons in its nucleus. If we were to produce some chemical reaction to remove a proton from carbon, we would be given boron, which is going to be the 5th element on the periodic table. Now there's also the concept of mass number. The concept of mass number refers to how many protons and neutrons are found in an atom's nucleus. So another way we could say this is how many particles, protons and neutrons, are found within the nucleus of our atom. So very oftentimes we will find that we actually have the same amount of neutrons as we have protons. So carbon, for example, again, its atomic number is going to be 6. And there's also going to be 6 neutrons that are found within our carbon atom's nucleus as well. So the mass number, or the atomic mass that we will say, will be 12. The mass number is going to be 12 because there are going to be 12 particles in this atom's nucleus. So, as I mentioned before, the amount of protons determine which atom we are talking about. So as long as we have 6 protons, we're going to be referring to some type of carbon atom. Now that being said, we can differ in the number of neutrons that we have. So there is something in the universe known as carbon-13. And that is going to be carbon that has 7 neutrons found in its nucleus. So you can see here that we have 6 protons and 6 neutrons. This is carbon-12. This is how carbon is most normally going to exist. But it's possible that we can have a 7th neutron that has been put into this nucleus, and that would give us carbon-13. So depending on how many particles we find in our atom's nucleus, that's going to tell us what the mass number is. So again, you can see that this mass number here is 12. When two different versions of the same element differ in the amount of neutrons they have, we're going to call those isotopes. So what we know so far is that if we change the number of protons within an atom, we change the element itself. But if we change the number of neutrons within an atom, that's going to be called an isotope. And so carbon-12 and carbon-13 are isotopes with one another. So this is a very nice picture to help us go through here. We have a few different elements that are placed in. We can see different atoms of different elements in front of us here. So we're going to touch on a few of the concepts that we can see. So once again here, the atomic number of hydrogen is 1. Again, if you go back and you look at the periodic table, you'll see the H is the first one. That is hydrogen. That means we're going to have a single proton in our atom's nucleus, and that's all a hydrogen atom is. It's just a single proton. So protons and hydrogens are the same thing. Now, most of the time we're going to have the same amount of electrons as we will protons. Now this can also change, but for simplicity's sake as we go through this, for right now we're going to look at all of these with an equal number of protons and electrons. So most often, like I said, we'll have the same amount of electrons per number of protons. So hydrogen has 1 proton, so a neutral hydrogen atom will have 1 electron. Now this can change. We can take away an electron, we can add an electron or something like that. But that is we'll talk about that in a little bit here. Carbon is another good example. We can see atomic number of 6. We did this one on the last slide. We have our atomic number of 6, and there's going to be 6 electrons in the electron cloud. So we can count these out. We can count 1, 2, 3, 4, 5, and 6. That's going to denote our 6 electrons that are found in the cloud that are going to be canceling out the positive charges of our protons. So remember, protons have positive charges, the electrons have negative charges. So when we put those together, we're going to get a neutral atom. Nitrogen, you can see here, has an atomic number of 7. So this one's going to be found right after carbon. So nitrogen is going to have essentially 7 electrons in its electron shell. So we can count these out. 1, 2, 3, 4, 5, 6, and 7 for 7 protons. So every neutral nitrogen is going to have the same amount of electrons and protons. And as I said earlier, oftentimes the amount of neutrons will be the same as the amount of protons. So you can see that carbon is going to have 6 neutrons, nitrogen is going to have 7, and oxygen is going to have 8. This can, again, differ, and this can give us different isotopes. You can see that the mass number can either be 16, 17, or 18. So we could either have 8, 9, or 10 neutrons, depending on which isotope of oxygen we're referring to. So why don't we do one more example? Because I will be referring to this picture in a little bit. We're going to use this as we talk about chemical bonding. But why don't we go over sodium here? So sodium again has an abbreviation of Na, and it has an atomic number of 11, which means that there are 11 protons in sodium's nucleus. You can see 11 protons. Now sodium's a little different. It's going to have 12 neutrons, and again this can differ, but we're just going to call these isotopes. So sodium will most often have 12 neutrons in its nucleus. But in for a neutral sodium, which is what we see here, if we have 11 protons in the nucleus, we're going to have 11 electrons in our electron cloud. So let's go ahead and count these as well. We're going to count these based on the rings that we see here. So we'll start and say 1, 2. So there's 2 in the first ring. We're going to go to our next ring. 3, 4, 5, 6, 7, 8, 9, 10. And then we're going to go to the third ring, and that's where we get our 11th electron. So there are 11 electrons and 11 protons in every neutral sodium. Now another concept that I want to touch on with this slide here is that I just mentioned those little rings here. So you can see that hydrogen here has what is called the first electron shell, and carbon has what's called the second electron shell. So electrons, as I mentioned, are existing in this electron cloud. And there are different energy levels at which our electrons can exist within. And those energy levels are referring to these different shells. So our electrons are always going to be found in one of these electron shells. And the goal of our atoms is to fill up these electron shells as we get more and more and more electrons. So for example, our first electron shell is always going to fill up first. The first electron shell can house 2 electrons. So as we look at hydrogen here, hydrogen's only going to have 1 shell because it only has 1 electron. But if we can see carbon here, we can have a maximum of 2 in this first electron shell. So you can see we have 2, and all of the other electrons are going to now form this second electron shell. So the electron shells are going to be very important for chemical bonding. So as we look at these, we have our first shell here, and we have our second shell, and based on the amount of electrons, we can have up to our 5th electron shell, and so forth. But one thing that we can mention here is that every atom is going to have what's known as a valence shell, and a valence electron shell. Now the valence shell refers to the outermost shell on any given atom. So for example, hydrogen's valence shell is the first electron shell. Carbon's valence shell is the second electron shell, and sodium's valence shell is going to be the third electron shell. So whichever electron shell is going to be the outermost shell on a particular atom, that's going to be what's known as the valence shell. And I will touch on the valence shell in just a little bit and why that is so important. It's going to be vital for forming new chemical bonds. So I'll explain that in just a little bit. So when our atoms are going to gain protons or lose protons, for example, that's going to change the element that we're looking at. If we change the amount of neutrons that are found within any atom, that's going to give us an isotope. But if we change the number of electrons, that's going to be called an ion. So an ion is any atom that has lost or gained an electron from or to its shell. So as we will look at these, this is how chemical bonding is going to be based on. And we will really be learning a lot more about ions, and we're going to be talking about ions a lot in this class, because there are many different ions that are going to be necessary for different body processes. So some other terminology for us here, I'm going to use this word quite a bit, is molecule. So oftentimes we will have individual atoms that will come together to form, and they'll form a bond between the two, and then they become this one structure. That's a molecule. If we were to take two hydrogen molecules and we were to link them up by sharing their electrons, that's going to now form a hydrogen molecule. That's no longer a hydrogen atom, that is now a hydrogen molecule. A compound is going to be a type of molecule. However, it's going to include more than one type of atom. So, for example, more than one type of element, I should say. So, a compound would be something like sodium chloride. Sodium chloride is also commonly known as table salt. So that delicious stuff that you put on your French fries is going to be sodium chloride. That is table salt. Table salt is a compound because it is a substance that is made up, it's a molecule that is made up of two different types of elements. So a molecule is two different atoms, and it doesn't matter what elements those atoms belong to, but just two atoms that have come together to form some type of bond. Compounds are referring to different molecules that are made up of two different types. So for example, a hydrogen and an oxygen can come together, and that would be a compound. So these are some examples of ions that we do find within our bodies. Hydrogen ions are going to be very common ones that we see. Now, a hydrogen, for example, hydrogen has one proton in its nucleus, which means it's going to have one electron in its nucleus. And a neutral hydrogen will have one electron in our electron shell. I think I said nucleus. The electrons are actually found in the electron shell, so don't let that confuse you. If we were to lose that electron, we would just have a proton floating around, and we could also call that a hydrogen ion. So a sodium ion here, a sodium ion is going to have, again, lost an electron, and that's what gives these positive charges. So we will call these cations. Cations are ions that have a positive charge. They have more protons than they have electrons. Anions, on the other hand, are going to have more electrons than they will have protons. So if we gain an electron into our atom, that's going to give us an anion. So the hydroxide ion is another one we're going to see as we learn about acids and bases. This is a hydrogen and an oxygen that have been bound together, and this is going to have more electrons than there are protons. So this is one example of an ion. However, this is an anion that just refers to a negatively charged ion. Cations refer to positively charged ions. So we will go through some of these. We're going to see lots of chloride ions this semester. We're going to see hydroxide ions. We're going to see calcium and sodium and hydrogen and potassium. We're going to be dealing with a lot of these different ions as we go through this course. On this slide, I don't want you to worry too much about memorizing all of these different ions and what their symbols are. I just want to give you an idea with this slide that our ions are going to have either gained or lost an electron. And so again, in review here, if we lose or gain a proton, that changes our element. If we lose or gain a neutron, that gives us a different isotope. If we lose or gain an electron, that gives us an ion. So I know that terminology might be a little confusing at first, so it's imperative that you guys are making sure that you're understanding the difference between those three different terms. So again, now that we've gone through that, I would expect that you guys could know a little bit more about this periodic table, that this is going to make a little more sense than it did the first time I showed it. So again, what can we see here? Any neutral hydrogen is going to have one proton, and that means it's going to have one electron. Any neutral carbon is going to have 6 protons, so that will mean that it will contain 6 electrons. And if we were to lose an electron in this carbon, that would give us, for example, a carbon ion. We also have oxygen here. Oxygen is going to have 8 protons and 8 electrons. So oxygen oftentimes it's called what's very electronegative. Oxygen really likes electrons. So oftentimes what oxygen will do is it's going to pull an electron from somewhere else, and it will often exist as an oxygen ion. with a negative charge. So atoms can form bonds with each other. That is where we get molecules. When two atoms come together and they form this connection between them that gives us a larger structure, or two atoms we call a molecule. Now, bond formation is pretty much dependent upon how many electrons is going to be found in our element's electron shell, or the valence shell, we should say. So the amount of electrons that are found in our atom's valence shell is what determines the likelihood that our atoms will form bonds. And this is going to bring us into this idea of the octet rule. The octet rule requires a condition known as stability. So when we get to understand, certain molecules and certain atoms are going to be more stable than others. And so this octet rule states that in order for our atoms to be stable, we want to fill up the entirety of our atom's valence shells. So for example, if we were to think about hydrogen that has a single proton, that's only going to have one electron here in its first valence shell. So hydrogen's really going to want to have that second electron, and that's going to give us a much more stable version of that atom. Now, I'm going to just tell you that there can be two electrons found in the first electron shell, and there can be 8 electrons that are found in the second electron shell. So the atoms that we're going to be playing around with in class are either going to want to have 2 in their first shell or 8 in their second, depending on how many electrons our atoms have. Now, of course, this cannot always happen. We don't always have the 8th electron to give, but this is what's going to determine the likelihood that we're going to form different bonds. So the 3 types of bonds we're going to talk about today are ionic bonds, covalent bonds, and hydrogen bonds. So as we look at carbon here, carbon is a very, very special, element that we're going to learn a lot more about in this class. But carbon, as I mentioned, is going to have 6 protons, which means a neutral carbon will have 6 electrons. So we fill up the first 2 electrons here in this first electron shell, and then we're going to funnel the other 4 here in this second electron shell. But let's go back up here and we'll look at nitrogen. Let's say nitrogen here is going to have 7. It's going to have 7. So we're going to go back to this picture here, and what we can see is that nitrogen is going to fill its first 2 in this first electron shell, and then it's going to dump the other 5 here. Oxygen with an atomic number of 8 is going to have 8 electrons, so it will have 2 in this first shell, and in oxygen's second or valence shell, we're going to have 6 electrons. You can see that sodium's atomic number is 11, and that's where we get to the third electron shell, because 2 electrons in the first, 8 electrons in the second, and that gives that last electron to come out here to this third shell. Excuse me. Now again, like I said, however many electrons we have in our atom's valence shell, that's going to determine how likely it is for us to form a bond. So we get into this idea of what is known as electronegativity. Electronegativity is a condition that our atoms exhibit that states that certain atoms will really want to fill up their electron shells. So again, when we go back up to our periodic table, when we see our periodic table, the further towards the right, the further to the right we go, I'll draw a little arrow here so you can see what I mean. The further towards the right we go in this periodic table, the more electronegative we get. So the idea of this is that oxygen is only going to be 2 electrons away from filling up its second electron shell. So oxygen is going to want to pull on other electrons more than others, more than carbon, for example. Carbon is very, very far away from filling up its second electron shell, so it's going to pull a little less hard than oxygen does. So chlorine is going to be an example that we have here. Chlorine is very, very electronegative because all it needs is 1 more electron to fill up that second electron shell. Oh, I'm so sorry. That third electron shell. Chlorine has a third electron shell. It only needs one more electron to fill up its third electron shell, and then it will have achieved the octet rule. So we'll have a full octet with our chlorine if we can get one more electron. And this is going to be the basis for lots of different bonds that we see. So for example, we're going to look at the ionic bond here first. An ionic bond is a bond between some type of cation and some type of anion. Remember, a cation is a positively charged ion, and an anion is a negatively charged ion. So we can see sodium is shown right here. Sodium is number 11 on the periodic table, so it will have 11 protons, and therefore it will have 11 electrons. So we can count these: 2, 4, 6, 8, 10, 11. This is our sodium atom. So the concept of ionic bonds is referring to two different atoms that are going to donate their electrons. Essentially, sodium is going to give its last electron away because sodium doesn't want to have this electron. Sodium is very close. It was happy with its octet when it only had 10 electrons, but it has this 11th one. So we want to be able to get rid of this last electron, and something's going to need to take that electron away from sodium. So that is where chlorine comes in. This is where we're going to get sodium chloride, which is our table salt. So this is the chemical reaction that forms our table salt. You can see that if sodium is going to donate one of its electrons, if sodium donates this outer electron here, that's going to leave it with 10. But remember that sodium has 11 protons in its nucleus. So if we have 11 positive protons and we only have 10 negative electrons, that's going to give us an overall positive charge on the entire atom. So you can see that the new sodium has been drawn here. This new sodium has 10 electrons and it has a positive charge because there are 11 protons found in its nucleus. Chlorine, on the other hand, is number 17 on the periodic table, which means it has 17 protons, and therefore a neutral chlorine is going to have 17 electrons. So chlorine, as I mentioned, is very electronegative. It really wants one more electron, and this is why sodium and chloride go together so well. It's because sodium doesn't want this electron, and chlorine does. So sodium can easily donate this electron to chlorine. You can see in chlorine's third electron shell here, we have 7 valence electrons. That's 1, 2, 3, 4, 5, 6, 7. I've just counted the electrons in the outer shell. All of the other shells below this have achieved the octet. So we want to be at the octet. That is what we are shooting for here with our atoms. So chlorine here, you can see, accepts this electron. This is the same electron that was donated from sodium. Sodium's going to donate this electron, and it's going to come all the way over here to chlorine, and then it's going this electron is going to be taken up by chlorine. Now chlorine, for example, is going to have 17 protons in its nucleus. If we take this other electron here, we now are going to have a chloride ion, and that's going to give us a negative charge. So we've formed a positive charge on our sodium ion. We formed a negative charge on our chlorine ion because we have traded the electron from one particle to another. And this is what sets up the concept of ionic bonding. Positive charges and negative charges attract each other. And because this whole molecule has a positive charge and this whole molecule has a negative charge, we're going to get our positive and negative charges attracting one another to give us what is known as sodium chloride. So this is an example of an ionic bond. Now again, I understand that some of these concepts might be a little challenging at times, so I have posted a YouTube video here. This is a Khan Academy video. I adore Khan Academy. They helped me get through many tough concepts, and they can do the same for you. So if you are struggling with any of these concepts, always feel free to reach out to me by email, or you can go ahead and watch this video here. And this will walk you through the concept of ionic bonding. Covalent bonding is going to be our second type of bonding. Covalent bonding refers to the sharing of electrons. So on the last slide, ionic bonding was donating electrons. Now we're going to be sharing electrons. And this is where we're going to have the essentially equal sharing of our electrons. So covalent bonds can exist in single bonds, double bonds, or triple bonds. So let's look at this first example here. Hydrogen. Hydrogen is number 1 on the periodic table. So hydrogen is going to have 1 proton, and therefore a neutral hydrogen will have 1 electron. So both hydrogens want one more electron in their valence shell. Remember, we can have 2 electrons in this first valence shell. So we want to be able to have 2 in each of these. So we can't do an ionic bond here. We can't donate electrons because both of these want to have 2 in their valence shell. We don't have enough electrons for everybody to go around. But what we can do is we can share electrons between these 2 atoms. So what essentially is going to happen is this electron is going to exist in both this electron shell and this electron shell. We can see that right here. These atoms are going to get very close, and they're going to share these electrons between the 2 of them. And that's going to be just satisfying enough for the both of them to form this molecule. And now the way we will look at this is each atom now has its octet met. We will say that these 2 electrons are going to fulfill the octet of this hydrogen, but they will at the same time fulfill the octet of this hydrogen over here. So this is our hydrogen H2 molecule. The same thing can happen here with oxygen, but this is going to give us what's known as a double bond. So oxygen is number 8 on the periodic table, which means that in a neutral oxygen, we'll have 8 electrons. We can count these. 1, 2, 3, 4, 5, 6, 7, 8. So we have 8 electrons in our oxygen atom. And in the valence shell, we're going to have 6. So we want to have 2 more. And that is the same for all neutral oxygen. We want to have 2 more electrons in each of these shells. So 2 of these electrons for each of these oxygen molecules are going to get shared. So you can see these are going to do a little extra sharing here. And so we're going to share 4 total electrons between the 2 of these. And that is going to complete the octet for oxygen. So you can see we have 1, 2, 3, 4, 5, 6, 7, 8. And over here we have 1, 2, 3, 4, 5, 6, 7, 8. Now I'm including the 2 here in this first shell here. So you'll see that there's 10 electrons that will be between each of these. So you can see in this first shell we'll have 2, and in this shell, the second valence shell, we're going to have our full 8. So the same thing can occur here with oxygen. Oxygen is number 8 on the periodic table, and therefore in a neutral oxygen we're going to have 8 electrons. So you can count these up. 1, 2, 3, 4, 5, 6, 7, 8. So each oxygen is going to have 8 electrons found in its electron cloud. So this valence shell is going to contain 6. You can count these. 1, 2, 3, 4, 5, 6, which means that this oxygen is going to want 2 more electrons. Well, at the same time, this oxygen is going to want 2 more electrons. So they can come together and they can share 4 electrons between the 2 of these. So we can count up the valence shells here. We can count 1, 2, 3, 4, 5, 6, 7, 8. That's going to fulfill the octet of both of these oxygens because both of these will now have 8 electrons in their valence shell. To make things even more exciting, we can do this with nitrogen as well and form what's known as a triple bond. So nitrogen is going to be number 7 on the periodic table, so therefore neutral nitrogen will have 7 electrons. You can count these up, but again, the same concept is true. We can share 3 groups of electrons between the 2 of these, and these will fulfill the octet of each of these nitrogen molecules and give us what is known as a triple bond. So you can see how we draw these out in chemistry. You guys won't need to do any of this drawing, but you can see we denote these with 3 lines, we denote the double bond with 2, and so forth. So the covalent bond is the sharing of these electrons. These 2 oxygens have come together and they've agreed that these 4 electrons will belong to the both of them. And that's what gives us a covalent bond. So the ionic bonds are the donation of electrons. Covalent bonds are the sharing of electrons. This is another example of covalent bonds here when we can have actually more than one different atom coming together here. So let's look at this example here. This is going to be water. Water is going to be H2O. You've all heard of H2O before. That is the chemical symbol for water. So we're going to have 2 hydrogens and 1 oxygen. Oxygen having 8 electrons in its electron cloud, and hydrogen having 1. These are going to come together, and they're each going to share. So oxygen's going to offer 1 electron to each of these hydrogens to complete their octet, and the hydrogens are going to offer their electrons to oxygen, and that's going to complete oxygen's octet as well. So you can see right here we have our water molecule that is in this position right here. And you can count the octet of each of these for their first and second shells. The octet will be met based on the first or second shell. So again, just as a reminder, the first electron shell can have up to 2 electrons. The second electron shell can have up to 8. The other example we see here is methane. Methane's molecular formula is CH4, so 1 carbon and 4 hydrogens. So you can see we'll take 4 hydrogens and we'll combine them with a carbon, and that's going to give us methane. So carbon has 6 protons in its nucleus, which means it has 6 electrons in its electron cloud, and therefore needs 4 more electrons to come along and fulfill the octet of carbon. So each of these four hydrogens are all going to share an additional electron here with carbon, and that's going to give us what we know as methane. So if covalent bonds are giving you a hard time, there's another Khan Academy video for covalent bonds here. So this is your resource. But again, if any of these are giving you guys a hard time, feel free to email me, and I'd be happy to give you another explanation on these. So our next type of bond is the hydrogen bond. The hydrogen bond is not really referring to the actual connection of 2 different molecules or atoms. There are many places that hydrogen bonds are going to help in the formation and aid in the formation and shape of different molecules, but these are going to be much weaker bonds. In order to understand hydrogen bonds, however, we need to understand the concept of polarity. I'm going to go back to this slide to understand the concept of polarity. So a molecule that is considered polar has an unequal distribution of charges throughout the molecule. So what we see here, we're going to use water as an example because water forms hydrogen bonds. One thing that I can note here about water is that the first electron shell here around this hydrogen is a little bit more warped than it is up here with methane. And it's interesting to note why this is. So this is not just drawn for animation purposes. There's actually a reason that this electron shell here, this valence shell, has been sort of warped and made sort of in the oval shape. Remember back to what I said about electronegativity. The further towards the right on the periodic table we go, the more electronegative we become. Oxygen is very electronegative, and therefore it has a stronger pull on the electrons that it is using. And hydrogen has a weaker pull. These electrons here, while being shared between the two of these molecules, they're going to be spending a little bit more time around oxygen. So this is where we get into the idea of unequal sharing of bonds. So the electrons here are going to house 2 negative charges. These 2 red electrons are going to have 2 negative charges. Now hydrogen is going to have a single proton found within this atom's nucleus. So if we have a single positive charge over here, and we have two negative charges here, but they're going to be found a little closer over here towards oxygen, that's going to give what is known as a partial positive charge. That's what this little symbol here with the plus stands for. This is standing for a partial positive charge. And we have the same thing happening with the other hydrogen as well. Because oxygen is pulling the electrons closer to its own nucleus, and that is essentially causing these negatively charged electrons to spend more time around oxygen. And if we're having all of our negative particles in this molecule spend all their time in one spot, that spot is going to be a little bit more negative than the other spots throughout that molecule. So polarity refers to this idea of unequal sharing of bonds, and that produces this phenomenon of partial positive and partial negative charges. You can see that this symbol here with the negative sign depicts that oxygen is going to have a partial negative charge. Well, this is rather interesting because if we have more than one water molecule, we now have water molecules with some areas are going to be positively charged, some areas are going to be negatively charged, and so forth. And this sets up the stage for hydrogen bonding. So remember here, the partial positive charge exists next to the hydrogen, and the partial negative charge exists next to the oxygen. So when we go to this picture here, you can see hydrogen is going to be having this partial positive charge, and oxygen is going to have the partial negative charge. It's not necessarily drawn in here, but you can see that on this one, we see the partial negative charge next to oxygen. So this partial positive charge is now going to be attracted to our partial negative charge. And so this is kind of a grand idea, but this is what gives us the phenomenon of hydrogen bonding. So our positive parts of the molecule are going to be attracted to the negative parts of other molecules. That's how this is going to be set up here. So this is going to be negatively charged here. This is positively charged, and those are going to be attracted to each other. Water is not the only molecule that can form hydrogen bonds, but it's the one that we will use and see most often forming hydrogen bonds. Hydrogen bonds give water the property known as cohesiveness or cohesion. Cohesion refers to the tendency of like particles to stay together. So what phenomenon this brings about is what is known as surface tension. So cohesion, again, we can see here that cohesion is defined by our like particles staying together, their tendency to want to stay together. So that is all found here due to the hydrogen bonds. Hydrogen bonds give us the ability for our water molecules to want to stay together. And because of hydrogen bonds giving us this cohesion, this also sets up the stage for what is known as surface tension. Surface tension, you can see explained here, is referring to how difficulty it is to break the surface of a liquid. And I've posted this picture here to show you surface tension, because you can see that this mosquito is able to stand on this liquid substance. So you can see that right here, it sort of looks as if the water is forming this barrier, and this insect's leg is pushing into the water. And this is due to surface tension. Essentially, the weight of the mosquito is not great enough to break the bonds between these hydrogen bonds between our molecules. So hydrogen bonds are very, very important because they give us things like surface tension. They help keep water together, and that gives the properties of water that are so vital for life. I'm going to pull this slide again from our last presentation, the concept of catabolism and anabolism. So remember, this is the same slide I pulled from chapter 1. Catabolism refers to any type of chemical reaction that's going to crush or break down large molecules into smaller molecules. And anabolism refers to any molecule that's going to build up or assemble small molecules into some type of large molecule. So these two reactions are reverse reactions of each other. Catabolic reactions take large particles and break them up into smaller particles. And anabolism takes smaller particles and builds them up into larger particles. This is going to be a theme here when we're talking about chemical reactions. Chemical reactions are going to be referring, sometimes we're going to be rearranging our molecules here or there, but oftentimes we're going to take simpler molecules and combine them to make more exciting or more diverse molecules. So the idea of catabolism and anabolism are going to be very integral here for our understanding of chemical reactions. So this reaction here we can see is taking some substituents over here, and it's rearranging them to give us these. So we're taking some simpler molecules over here, and we're going to break these bonds, and that's going to be a catabolic reaction. But we're eventually going to build them back up into water molecules, and that's going to be anabolic. So this whole reaction will be an anabolic reaction that we see progressing from left to right. Now, with every chemical reaction, there's going to be some starting substance, and then, of course, we're going to have some type of ending substance. So whatever the starting substance is are going to be the reactants, because they are producing the reaction. And lastly are going to be the products, because they are what come out of our reaction. So you can see every chemical reaction is going to be written with this little arrow to depict the direction of the reaction. So these products are going to become these products through an anabolic reaction. Now, with every chemical reaction, energy transfer is going to be vital. Energy is very, very important when we talk about anatomy and physiology, when we talk about chemistry and physics. Energy is very, very important. So what is energy? Energy is the capacity to do any type of work. So the ability, there's lots of energy that's going to be stored in the bonds of our molecules. And when those molecular bonds are going to break, that's going to release energy. And then it's going to require energy to put those bonds back together. So there are a few types of energy that we're going to mention. We've got potential energy. Potential energy refers to any type of energy that is based on something's position. So for example, if I was to put a bowling ball at the top of a set of stairs, that would have a lot of potential energy because all I'd have to do is roll that bowling ball off the stairs and then it would progressively fall on its own. While kinetic energy is the energy of movement. So as I push that bowling ball down the stairs, that potential energy gets converted into kinetic energy. So energy is never going to be created or destroyed. It's only converted into one form from another. And that refers to the law of conservation of energy. So this is a physical law that states that energy cannot be created or destroyed. It can only be changed from one form to another. And that's why when we think about our bowling ball at the top of the steps, that's going to have a lot of potential energy. And we don't lose that potential energy. We just convert that potential energy into kinetic energy as the bowling ball falls down the stairs. So our form of energy that's going to be important for our class is chemical energy. And this is the type of energy that's stored in our molecules' chemical bonds. Now there are many different types of chemical reactions, and this idea of exergonic and endergonic reactions tends to be a little dense. There's a lot of information in your book about these, but all I want to mention here about these is what you see on this slide. So exergonic reactions tend to release more energy than they absorb into their bonds. So we often will refer to these as catabolic reactions. Our catabolic reactions are most often going to be exergonic reactions because they're releasing more energy. And that energy can be captured and converted into other things. But as nutrients are broken down and bonds are broken between two different atoms, that's going to be releasing energy, and we call that catabolism. Now the opposite is here with our anabolic reactions. So endergonic reactions are going to absorb more energy than are released. So if we're absorbing more energy, that's going to be required to create bonds. And so that's why we will refer to these as anabolic reactions. So nutrients are being built up as we take molecules and combine them, and we take these molecules and form new bonds. And that is called anabolism. And so these are going to be absorbing more energy into the molecule and therefore are called endergonic. One of the other major players here in chemical reactions are what are known as catalysts. Catalysts are different chemicals that function to speed up chemical reactions. And we often refer to catalysts as enzymes. So we're going to learn quite a bit more about enzymes throughout the course of this class. But what catalysts are going to do and what enzymes do is they speed up the time it takes for a reaction to progress. So some reactions that might have taken days or weeks to progress, with the help of enzymes, can progress in seconds. So catalysts are another very important concept, and they're going to be very necessary for speeding up chemical reactions. So another type of chemical reaction that we're going to mention is the oxidation-reduction reaction, which can also be called the redox reaction, hence the abbreviation here, RED and OX. That stands for redox. So an oxidation-reduction reaction refers to some type of reaction where electrons are transferred between one molecule and another. This refers to what is known as an oxidation and reduction of our different molecules. So one molecule, while we transfer electrons from one molecule to another, one molecule is going to be reduced and one molecule is going to be oxidized. So let's define these, oxidation and reduction. Oxidation, it refers to the loss of an electron. So anytime our molecule loses an electron, it is oxidized and it is lost an electron. So anytime a molecule undergoes oxidation, that just means that it loses one of its electrons. If we lose an electron on a molecule, that is going to be an oxidation, while the reduction is referring to the gain of electrons. Now this might be a little confusing because when we reduce something, we wouldn't think that we're gaining anything. But when we say a reduction, we're talking about the overall charge of the molecule. So if we're gaining electrons, we're adding negative charges and therefore decreasing the overall negative charge, the overall charge of our molecule. So that's why a reduction refers to the gain of an electron, because when electrons are added to something, they decrease the overall charge. Now, electrons are also going to be associated with energy. The more electrons we have in a particular molecule, the more energy we're going to have. So if we lose electrons and we oxidize a particular molecule, that molecule is going to release energy, and it's going to be less energized than it was before. While if we are reducing our molecule, that's going to cause the gain of energy, and our energy is going to be more, our molecule is going to be more energized than it was before. So one way that you can remember oxidation and reduction is the nice little mnemonic oil rig. So I'm going to write this down here for you. Oil rig. This is one of the little tricks that they teach you in chemistry class to remember oxidation and reduction reactions. So oil rig. Sorry, it still takes me a little while to write these down. I'm still working on my penmanship over Panopto here. So oil rig. Why on earth did I just write this? You guys might think I'm going crazy or something. So oxidation is the loss of electrons. Reduction is the gain of electrons. So what oil rig stands for? Oil rig is oxidation is loss, and reduction is gain. So that's how you can remember. This little mnemonic here will help you to remember which one is going to be losing electrons and which one's going to be gaining electrons. So reduction is gain and oxygen is loss. So oxidation is loss, reduction is gain. So this is the way you can remember oxidation reactions. So every redox reaction is going to occur in parallel, which means that while something is going to be oxidized, something else is going to be reduced. By definition, an oxidation-reduction reaction is the transfer of an electron from one molecule to another. So if we are transferring it from one to another, we have to have two different molecules. Something's going to be losing that electron, and something's going to be gaining it. So in the example here, we have two molecules. We have molecule A, or atom A, and we have atom B. And you can see that atom A has this electrons, which means that it is reduced. It has an electron. So this is a reduced molecule here, and this is an oxidized molecule because it doesn't have any electrons. And through this redox reaction, as we progress, we're going to transfer this electron from A to B. And as we transfer this electron from A to B, the energy housed within this electron is going to be transferred with it. So A, in this reaction, you can see that A here has the electron, and then over here it doesn't because it's been transferred to B. So A, in this example, is oxidized, while B, which has gained the electron, is going to be reduced. Because, again, the overall charge of this molecule is now one charge less than it was before. So reduction is the gain of electrons, oxidation is the loss of electrons. And so what I mean when I say that these reactions occur in parallel is that means that as one thing is oxidized, something else is going to be reduced. So the oxidation-reduction reaction will always occur in parallel. When one thing is oxidized, something else will become reduced. So this will take us into inorganic and organic compounds. And what are the difference between these different compounds? Why do we refer to them? Why do we have organic and inorganic chemistry? Well, we're gonna talk a little bit about these different types of compounds. So the most notable characteristic about an organic compound is that it will always contain carbon. Organic compounds must contain a carbon atom. If it doesn't have carbon, it's not organic. Oftentimes, our organic molecules will contain hydrogen as well. So carbon and hydrogen molecules will be often connected through covalent bonds. So if you see a lot of carbons and hydrogens together, odds are that it's going to be an organic compound. Inorganic compounds are typically going to be much smaller molecules. These are going to be a little bit more simple, and they tend to lack carbon. So these are not going to have as much carbon in them. Water is one example of an inorganic compound. Water is going to be H2O, so it doesn't have carbon, but it's going to be very, very small. It's going to be a very simple molecule. However, it is so vital for life. So that's the major difference between inorganic and organic. So again, here on this slide, we're just explaining the idea of polarity once again. So on the last time I explained polarity, we see that we have these electrons are going to be pulled more towards oxygen. And that gives the partial negative charge to oxygen in this part of the molecule. And the partial positive charge is going to be over here by hydrogen. So this is just a little bit of a review from what I talked about earlier. So water is a very, very, very important molecule. Water acts as what is known as a solvent. So there's two terms I'm going to introduce to you here. One of these is solvent, and the other is going to be solute. So we have two new words here. We have a solvent and solute. What do these words mean? So a solvent is something that dissolves something else. So for example, if we live in the good old South, so I'm sure that at some point in your life you've tried sweet tea. If you haven't, you should order it the next time you go out. It's delicious. So if you have tea's base is going to be water, but when you add sugar to your tea, that sugar is going to dissolve into the tea, and therefore the tea is acting as the solvent. So if we were to pour salt in water and stir it up, the salt would eventually dissolve into the water. So water acts as a solvent. The solvent is something that dissolves something else. While the solute in these examples is going to be the sugar or the salt. The solute gets dissolved. So the solvent always dissolves the solute. Water is a wonderful, wonderful solvent. You can see here in this example, we have a sodium chloride crystal. This is table salt. Because of water's properties, it's able to dissociate sodium from chloride. So when we see here is in solution, if we dump this into solution, a solution is just a mixture of a solvent and a solute. But if we were to dump some salt into water, what's going to happen if we were to really be able to zoom in and see what's going on there? We'd see that the sodium molecules are dissociating, and the chloride ions are going to dissociate. So we have the dissociation, but there's a difference in how water is going to interact with each of these. You can see that water's oxygen here with a partial negative charge is going to be oriented around sodium, while around chlorine, or the chloride ion, we're going to have these partial positive charges oriented around chlorine. So water does function as a solvent. Again, this is the idea of water being a very polar compound. It can interact with both positive and negative particles. So these next two reactions are going to be definitely the most important reactions we're going to talk about today. These are the hydrolysis reaction as well as the dehydration synthesis reaction. So these are going to be the two reactions that are going to be referred to as catabolic or anabolic and help us to build up our macronutrients such as proteins, carbohydrates, and lipids. So a hydrolysis reaction adds water and breaks bonds, while a dehydration synthesis reaction is going to remove water and make bonds. So, how are we going to keep these reactions straight? So, as we look at each of these chemical reactions, there's a few different indicators within the words that are going to tell you what you need to know. As I said in the first class, the terminology here in this course is so important. There are many answers that you can deduce correctly based on the type of abbreviations and suffixes that we can find in our words. So let's touch on that. So this is a hydrolysis reaction. Hydro stands for water, while lysis stands for bond breakage or cutting. When you lyse something, you are cutting or breaking something. There are immune cells that have lysozymes that will cut and break other different cells. So whenever you see this suffix here, lysis, we're referring to some type of breakage or cutting of something. So the hydrolysis reaction adds water and breaks bonds. Well, the dehydration synthesis reaction is going to remove water and make bonds. So dehydration refers to the removal of water, while synthesis refers to the creation of something. So that's going to refer to the bond. So let's look at these different reactions and see what we see. So one thing I want to mention before I explain this picture here is that these two molecules are not connected. I know this green circle makes it look like these two molecules are connected, but that's why I've placed a little plus sign in here so you can see that these are actually two different molecules. The green circle is tracking our water. So as you look at the green circle, we'll see water. However, these two molecules are not connected. So what we can see is we have glucose and fructose, which are two different types of sugar. You can see that the dehydration synthesis reaction progresses towards the right, and the hydrolysis reaction progresses towards the left. So with the dehydration synthesis, we're going to remove water and create new bonds. So this H2O, we have two hydrogens and one oxygen in this green circle. This is showing us water. If we remove water from this point in these two chemicals, that's going to allow us to create a bond and pull out water. So through the dehydration synthesis reaction, we can see that we've now formed a new type of sugar known as sucrose. And we've also formed water. So in progressing towards the right, we've removed water from each of these components, and we have made a new bond. You can see this new bond running through this oxygen here. Now, on the other hand, when we go back the other direction, the hydrolysis reaction refers to adding water in order to break bonds. So we're actually going to take these reactions can progress in the opposite direction. The dehydration synthesis and hydrolysis reactions are going to be opposites of one another, and they progress in opposite directions. So if we take this water and we add that water to this bond, that's going to give us a hydrolysis reaction. We're going to add water to the both of these, and we're going to break that bond. So the dehydration synthesis is going to remove water and create something. And that is known because of this name, dehydration for water removal and synthesis for the creation of. Hydrolysis is going to add water and break bonds, and that is noted here by hydro and lysis. So this is going to be an important suffix here, lysis, as we go through this class. So whenever you see this at the end of a chemical reaction, that means that some type of bond is going to be broken, is what lysis means. So as we continue to talk about water, I want to mention that water has very, very special properties. Some of the properties that we see here is that water has a very high heat capacity as well as a high heat of vaporization. So while these are important concepts of water, these can be found on page 40 in your book, and I'm actually not going to go over these. These will not be on your test, but I just wanted to mention that they are there for you, and you can look these up in chapter or on page 40. But the property of water that we do want to be mentioning here is water acting as a lubricant. So water is going to form the base of a lot of our body's secretions and fluids. And because water is a part of this, these fluids are going to help lubricate different membranes within our bodies. I mentioned the serous membranes in our last class and how our organs are able to slide past one another, and that is thanks to water here. The next concept we're going to touch on are mixtures. So mixtures are any combination of constituents, so elements or compounds, and mixtures are physically blended together. So these are not going to necessarily be bound to one another by any sort of chemical bond, but they're just going to be combined within the same. You can see the same glass here. So salt water is going to be one example of this. We don't actually form any connections between our water and our sodium and chloride particles, with the exception of those hydrogen bonds, but these are physically blended, not bonded together. So there are three types that we're going to mention. We have solutions, we have colloids, and we have suspensions. And each of these mixtures are pretty much going to be distinguished based on the size of the solute. So think back to those two terms I said, the solvent and the solute. The solvent dissolves something else, while the solute is getting dissolved by the solvent. So the size of our solute particles is pretty much going to determine which mixture we're looking at. So solutions are what are known as homogeneous mixtures. When we mix, let's say if we were to mix salt and water together. If we were to mix salt and water, eventually all that salt's going to dissolve and you're not going to see it anymore. And it still is going to look like one substance. That is what homogeneous means. It means that the whole mixture looks the same. So the solutions are going to have very, very small particles. Essentially, the particle size of our solute has become very, very small. Our colloids, on the other hand, are going to contain particles that are in between in size. So these particles are medium size. Our colloids have particles that are a little bit larger than they were in solutions. And this produces a murky substance. So Jell-O is an example of a colloid. There's very large colored particles in our colloids, and that's what makes our Jell-O somewhat translucent. It's not necessarily transparent like salt water is, but Jell-O is going to be translucent. For example, fog is going to be another depiction of a colloid because it's going to be a mixture of air and very large water particles. So both of these are examples of colloids. Suspensions, on the other hand, are going to contain very large particles. And in fact, their particles are so large that they never truly fully mix together. They will separate over time. So blood is an example of a suspension. Blood's constituents are made up of plasma as well as red blood cells. And if you let blood sit out for long enough, the red blood cells are all going to sink towards the bottom. So sand and water is a great example of a suspension. You can mix up sand and water if you put that in a bottle and you mix that up. For a very short time, the sand and the water are going to be all mixed up, and it's going to look like it might be rather the same throughout. However, after just a few seconds, the sand is going to settle on the bottom. So that is an example of a suspension. So what distinguishes solutions, colloids, and suspensions are the sizes of the particles that are participating in the mixture. So solutions have very small particles, which makes them homogeneous. Colloids are going to have medium-sized particles. These will also be considered homogeneous because they are still considered the same throughout. Fog and jello are the same throughout the entire structure, so therefore they will be homogeneous. However, suspensions are heterogeneous, which means that they are not the same throughout the entire solution. So the next major concept we're going to mention are acids, bases, and salts. So it's important to note when we're mentioning acids, bases, and salts, the concept of dissociation. So when something is added to a solution, such as sodium chloride into water, for an example, those particles are going to dissociate in the solution. So as we saw up in this picture here, we have a dissociation of our sodium and chloride particles. The chloride ions go over here and the sodium ions go over here. So these particles, while stuck together while it's sitting on your table, when you add it to water, those particles are going to dissociate from each other. And this is done in solution. So acids, bases, and salts are going to be other concepts that we're going to touch on in this class. So the way to tell if something is an acid, a base, or a salt is based on what particles it's going to dissociate into in solution. So all acids in the world will dissociate into some type of hydrogen ion and an anion. Every single acid will dissociate. This hydrogen ion will break apart here. You can see that this is hydrochloric acid. So when we drop hydrochloric acid into solution, this hydrogen is going to dissociate on one end, and this chloride ion is going to dissociate on the other. So any type of acid is going to dissociate into some type of hydrogen ion and an anion, a negatively charged ion. So because our hydrogen ions are positively charged, we must have an anion that's going to bind to that. Bases, on the other hand, will dissociate into some type of hydroxide ion and a cation. So any type of positively charged ion as well as the negatively charged hydroxide ion. So this example here is potassium hydroxide. K is the symbol for potassium. So potassium hydroxide will dissociate into a potassium ion and a hydroxide ion in solution. Salts, on the other hand, are going to dissociate into any type of cation and anion. So our example of a salt is going to be table salt. Sodium and chloride together are going to dissociate as long as they're not going to dissociate into H plus or OH minus. If they dissociate and release any of these, they are going to be considered an acid or a base. So in terms of what an acid is right here. This is what an acid is. An acid is just excessive protons found within a solution. Bases are excessive hydroxide ions that are found in solution. So when you are looking at something acidic, for example, lemon juice is very acidic, there's going to be a lot of hydrogen ions that are floating around in lemon juice. So the way that we form salts is we react a base with an acid. So if we were to take this acid, we were to take this base, we were to react them together, we would get potassium chloride. We would get potassium chloride, K and KCl, so the K and the Cl would match, and then we would get water. So when acids and bases react, that gives us some type of salt and a water. The pH scale is essentially used to measure the amount of hydrogen ions in a solution, how acidic something is. Now, I don't need you guys to be experts on the pH scale, but I just want to take a minute to explain how the pH scale works. The pH scale goes from 0 to 14. At 0, that's as acidic as something can get, while at 14, that is as basic as something can get. And 7 is going to be neutral. So the further towards 0 we get, the more acidic a substance becomes, while the further towards 14 we get, the further basic, and the more basic our substance becomes. So again, all an acid is something that releases hydrogen ions into a solution. And based on how many hydrogen ions are present, that tells us how acidic our acid actually is. On this slide, I have some examples of substances that have particular pHs. So we're not going to go through every single one of these, but I do want to mention a few of these that are interesting. So you can see urine here. Urine can range on the pH scale from 4.6 to 8.0. So if urine is particularly acidic, it can be closer to the 4.6 range. If it's rather basic, it can be 8.0. You can see coffee here is going to be acidic. Tomato juice is going to be acidic. Vinegar is going to be acidic. This is why a lot of folks use vinegar to clean their homes, because this is an acid. So this is just an example here. You can see gastric juice. Gastric juice is very acidic, so 1.2 to 3.0 on the pH scale. Gastric juice needs to be acidic. This is the essentially stomach acid that's found within the stomach. So gastric juice needs to be acidic because it's going to be breaking down and denaturing different proteins and other compounds. So there's a lot of body substance here that we can see, but the one I want to mention is blood. Blood has a very narrow range of pH that it can be within. So we say that blood is supposed to have a pH of about 7.4. So blood is supposed to be very, very slightly basic, just very, very slightly basic. And if we go any higher than 7.45, we can our blood can become too basic. If we go below 7.35, our blood can get too acidic. So it's very important that our blood remains in a very specific range. So there are some different body fluids here that you can see that have different pHs and such. Lye, for example, lye is not a body substance. Lye is sodium hydroxide. This is as basic as we can get. So sodium hydroxide is as basic as we can get. You can see at 14. So this is the component that people use to make soap. I don't know if we have any soap makers in this class, but that is the substance that we use to make soap. So as we're in the concept of acids and bases, that's also going to include our understanding of buffers. Now, buffers are very, very important because, as I just mentioned on the last slide, certain conditions in our bodies need to remain within a particular range. And so if blood gets too acidic, that could be a real problem. And so this is going to be regulated here by our buffer systems. So what buffers function to do is maintain the pH of a particular substance. Buffers function to resist and regulate pH. So if our blood becomes too acidic or too basic, that can denature proteins within our body. So denature is just a word for essentially destroying proteins. We're going to talk a lot about proteins in the second part of this presentation. But denaturing proteins is going to be one thing that can happen if our pH goes too drastically to either side, or things get too hot or too cold. So we have a few different buffers that are found within the body, but the one that I'm really going to mention here is the bicarbonate carbonic acid buffer system. So the way that this buffer is going to work is we have a few different molecules down here. We have carbon dioxide, which is CO2, we have water, which is H2O, and then we have this reaction symbol. So these two things can interact with each other, and they can combine to form carbonic acid, which is H2CO3. So that's the chemical formula for carbonic acid. But they can also be in equilibrium here with hydrogen ions and bicarbonate. So you can see bicarbonate is right here. So remember what I said about acids. Acids are protons. Acids are hydrogen ions. So if we are to increase the amount of hydrogen ions that we have in our bodies, this could potentially cause our bodies to undergo more acidic conditions. And if we get too acidic, this can be a problem. So this is where the bicarbonate buffer system is going to come into play here. If we increase the concentration of hydrogen in our bodies, and when I say concentration, I'm just referring to if we get more and more and more hydrogens in our bodies are going to become more acidic. So if we increase the concentration of hydrogen ions, those hydrogen ions are going to off-put this chemical reaction. The fact that we have an arrow pointing to the right and an arrow pointing to the left at the same time tells us that we're undergoing equilibrium. And what that means is we just have the same amount of these as we have these. So as we see here, if we get more hydrogen ions here, as we get more and more and more hydrogen ions, that's going to increase the acidity of our body. But that's also going to offset the equilibrium of this particular chemical reaction. So as we get more and more hydrogen ions, those hydrogen ions are going to start to combine with bicarbonate. And when hydrogen and bicarbonate become combined, that's going to form carbonic acid. And then thus, our entire reaction is going to shift in this direction. So if we add a whole bunch of hydrogens, we're just going to counter that by adding a whole bunch of bicarbonates that are already found in our bodies. That's going to form more carbonic acid and eventually more CO2 and more water, and this is going to function to keep our pH in a more appropriate range. So I'll actually be separating the chemistry lecture into two sections. I will be going into organic compounds in part 2 of this video here, and we will discuss carbohydrates, lipids, proteins, and nucleic acids. We're going to discuss their structure, and you guys will be responsible for that next week. So for now, that will conclude the second lecture video containing our fundamentals of chemistry. If you have any questions, make sure to come to me at any time. I'm here to help. If you need any other explanations on any topics or you want to go over this material, you have my office hour times and such. So I hope you guys have a good rest of your day, and I will see you in the next video for the overview of organic compounds.